Hello, Adam. It's your brother, and it is Saturday, March 2nd, 2013. Like I said in the last video, today I will be talking about speed limits, or talking about traffic, specifically regarding speed limits. Um, it's a fairly technical subject, but like speed limits will hopefully play, a significant role in the life of every driver on the road. Especially like when you're on the highway and sometimes you just gaze out into the open highway and you say, man, why can't I legally go faster than I'm going right now? Part of it has to do with, your car actually has a speed limit that it can't go faster than, but most of the time the speed limit is above that or below that. So let me explain how the government comes up with speed limits. First of all, if we're going to approach this using math, we need to define a few things. So we can only really use the following models if we're talking about a very specific set of conditions on our roads. Those conditions need to be that the highway has to be homogeneous for the area on which the speed limit is to be placed. That means there can be no change in the number of lanes, there can't be any on-ramps, and there can't be any off-ramps. Because we need to know exactly the kind of flow and number of cars on the road and their speeds at any given time approximately that we're talking about. And any of those lane changes, on-ramps, off-ramps, stuff like that, makes all of that uncertain. So we need to assume that there's nothing like that for the stretch of road that we're talking about, that we're putting a speed limit on. What that means is that the road looks the same at any point along that stretch. So we can ignore, basically, where we are on that road and only pay attention to the conditions at that exact point. So an engineer will look at this stretch of highway and say, alright, what do we need to make the speed limit? First, he needs to know how long that stretch is, and he needs to know the average vehicle length. That's not including semi-trailer trucks. Semi-trailer trucks follow a different set of rules on the road than regular vehicles, both due to the laws of physics and the laws that the government lays down. So they behave differently in traffic from other vehicles. I'm sure you've actually noticed that. So in order for this to work, we need to assume for the moment that the average vehicle length does not include semi-trailer trucks. So we also need to know the safe following time that he's going for. And I say following time, not following distance, because whereas a person's reaction time in a vehicle is relatively constant, assuming they're not texting or drinking, then that'll help us because it takes away the factor of speed in our equation. If we were to say instead, we wanted a following distance, then that would be a function of reaction time and stopping distance for the vehicle based on the speed. So once he knows those things, he can calculate the maximum speed that the fully utilized road, the maximum speed that the vehicles on that road can go while also maintaining that following time. And I could give you the equation. It's that velocity would be the length of that road divided by the maximum number of vehicles that are going to utilize that road at one time, and also divided by the following time that he wants to go for. And these are all things that he needs to know before he sets a speed limit. So he can set a speed limit. So now we're going to consider that traffic is in a certain condition, and that condition is what is called free flow. Free flowing traffic means it means that there's a certain density, like number of cars per kilometer or per meter or whatever you want, like a density of cars on the road, and based on that density, scaled by a factor of the velocity of those cars, you can calculate a maximum flow rate of cars, which will be in like cars per meter or cars per hour, whatever you want. And the condition of free flow is where that holds, where you can say, all right, I need 17 cars per hour to go through here, and based on the velocity that these cars will be going, this is how many cars per meter there are going to be, or cars per foot, or whatever you want. So based on that, if we set an equation of Q flow rate equals average velocity, which is a minimum velocity, mind you, in order to achieve this flow rate, average minimum velocity times the density of cars rho. And what happens is, since speed limits only care about we set the speed limit based on the condition where the road is fully utilized, we can determine the flow rate at which this is applicable by saying, oh, if the rho is equal to cars per meter and velocity, the velocity, speed limit velocity, is equal to distance divided by number of cars on the road times the following distance, then we need, first of all, we need to multiply that by the number of lanes that are on the road. And then we can substitute both of those into our equation Q equals V rho, and that'll eventually give us the only road condition at which a speed limit is actually useful for the road is where Q is greater than or equal to the number of lanes of that road divided by the ideal following distance. And that'll be in cars per meter. That's a flow rate. So the problem is, when we're setting a speed limit, yeah, that sounds all good and stuff. The problem is that there's a second condition of traffic which most people associate with the word traffic, which is congested traffic. Congested traffic by definition is just any traffic that doesn't meet the criteria of flow rate being proportional to density of vehicles. The more density vehicles get, the flow rate doesn't scale proportionally. And that happens because, I'm sure you're familiar with the phenomenon, as cars get closer and closer together, people become more and more cautious, and they slow down instead of speeding up, which is what they should do. Or which is what they should do if they want to continue keeping the flow rate high. What this means is that if we were to create a graph of the flow rate as a function of the density of vehicles on the road, then that graph would be increasing with a slope, the average velocity. However, once it reaches the point where people say, all right, this is like too close for me, and they start backing off and slowing down, the slope reverses and goes down again. So there's like a famous model, or famous among, I guess, traffic engineers. It's a model where if you're going to draw such a graph where flow rates on the y-axis and densities on the x-axis, or for you it would be, I don't know what I'm doing. This is right. Where this is, then the velocity will be the slope up to a point, and then people will decide to start slowing down, and it'll start going down, and it'll look like an upside down V. Now, since the only condition at which our speed limit matters is at the point lanes divided by following distance, which is it'll look like a horizontal line. If our graph never reaches that horizontal line because it starts going back down at a certain point, then the speed limit literally does not make a difference for congested traffic and should not be implemented, which is what some countries have figured out. Like Germany, where this book was written, they said, yeah, once you reach a certain point, you don't need a speed limit anymore because the cars wouldn't be going that fast at a heavy load anyway. They'd be slowing down once the load got heavier. And when the load is lighter, there's no congestion, and therefore you don't really need a speed limit because it doesn't make a difference how fast cars are going if they're not around other cars. In theory. At the end of the day, what this means for speed limits is that our government has a hard time taking measurements and calculating statistics and all this stuff on how many cars are actually going to be using the roads. especially since that changes a lot over time. Since we don't have like dedicated supercomputers sitting around crunching numbers with or getting like inputs from all of the highways and going, okay, we need the speed limits to be like this between these 2 points and this between these 2 points, and that needs to be different for like every stretch of the highway. Since we just don't have that infrastructure, the government has found numbers that generally work over a large number of cases, and they implemented those, which is why in Indiana you go 70 on the highways unless if you're speed limit 70 on the highways unless if you're like downtown, and then you go different speed because there's more flow. So as you can see, like I didn't even introduce any equations, and honestly I sat here like working with the equations for a very long time, and it's still a little baffling to me. One thing I will say though is that this is already a very long video, and I covered 6 pages of this 600-page book. So let me know if you find this stuff interesting. This is just sort of an introduction, the theory of free flow, which is the most robust and studied theory of traffic flow. There's actually 3 phases of traffic, one of which is free flow, and the other are 2 types of congestion. Yes, there are actually 2 different types of congestion that work fundamentally differently from each other. So I didn't even talk about those, but you know, I could introduce more mathematical models. I could show you the equations and how they work. I could use real numbers from real situations. So if you're interested in this sort of stuff, which I definitely am, that's what I've been actually doing for the parts of the day that I haven't been sleeping or being inspected. So just let me know if you want to know more of this stuff, because I've got plenty more to cover. And that is how speed limits are formed. Adam, it's been a long day for me. I will see you on the evens. Goodbye.